So we spent some time exploring how the different instructions the M3 offers and how they work. Kind of, we tried out examples of those. And one very specific kind of instruction that I left out was related to the stack manipulation. And that was deliberate, and that is what we'll explore now. So there are instructions like push and pop. So what these will do is push can put some registers um, on the stack, and pop can essentially, fetch back those values into the register. Right? So again, to make the imagination clear, we have these registers within the CPU and R0 through R15. So what we can do is we can save the value of these like multiple registers onto the stack, right? And the stack in case of the M class CPUs goes from like a top, let's say hex 1000 for example, and we have, let's say, hex I don't know, 0 here at the bottom. So the stack will kind of move downwards, right? So you're supposed to imagine it like stack of plates, but the gravity is upwards. Now pointing upwards, meaning the plates are pulled this way, and so it's an inverted stack, so to speak. As you add things to the top of the stack, the memory location available to you as the next top of stack is a lower address, right? So the first entry goes on hex 1000, the second one goes on the hex 1000 minus 4, and so on and so forth. So it's called a decrementing or descending stack, right? So that's the idea. And then these push and pop instructions are what I had left out deliberately. And what we'll do is run an experiment now and kind of discover as to how the push and pop operations work. And again, the reason we are investing our time into learning push and pop operation or understanding this assembly, what do you say, assembly instruction, is because when writing the scheduler, this is going to be one of the fundamental instructions that we use, right? Okay, so with that, let me go ahead and so we had this program from the last time. What I'm going to do is delete all of this, everything below the reset handler, and I have left the move instructions. So now what I'll do is I'll say push and then put curly braces and say R1 comma R2. So then R1 gets pushed first, R2 gets pushed next, and that way these values are now on the stack. And again, I'll draw some pictures to explain exactly how to imagine this. But then what I'm wanting to do is put some different numbers in the registers R1 and R2, and then go ahead and pop um, R2 and R1. Right? And then we'll just say branch indefinitely on the current line. Right. So the push instruction is here, the pop instruction is here. And this is, as we discussed previously, this is supposed to be the top of stack, right? Okay. So then what do we expect? What should essentially happen? So let me just go ahead and, okay, uh, give me a moment here. I'm just trying to change the color, which won't happen for God knows why. Okay, never mind. So we have this piece of memory here, and hex A, B, what was it? Hex A, B, C0 is this memory location, right? And we had R1 equals to 7, we had R2 equals to 3. Now, when I do push R1 comma R2, what should happen is it should decrement the stack by 4, populate the value of R1 here. So this gets R1, which is 7, then decrement the value again by 4 and kind of put the value of R2 here, which is 3. That is what should happen. Now, again, there are details about whether it decrements the address first and then loads the value, this, or it loads the value and then decrements. So from what I recall in my experience with this CPU is the stack pointer will be pointing to the current free word, right? What that means is the first value here, the first value R7 will go to the memory location hex ABC0, and the second one will go to hex ABC, hex A, think it would become, I think it would become this, right? That is what it should become. And we'll again, see this happening in the code. So let's not stress too much about what exact, memory location is it? Is it like the stack pointer address loaded first, like say populated first, and then the address, the value is decreased, the stack pointer value is decreased, or does it decrease first and then load the value? That we'll eventually discover. And just to reconfirm, right? There are certain processors which kind of decrement first and load the value next, but we'll just kind of verify our assumptions. Okay, but the key idea is that these values will go on the stack. And once that happens, what will happen further is we'll change the value of R1 and R2 to become 5, just so that we can visibly see the change, and then we'll pop out. And the pop operation then, essentially, so wherever the stack was pointing, we argued that it might be at hex A, B, B, C. So here we had the value of R3, so, which was 3. So this 3 then is loaded back into the R2, and then it decrements, the stack pointer decrements by a word, and then goes back to pointing to hex ABC0, which is R1 equals 7, and this 7 value is popped back into R1. So that is what the push and pop instruction is. Now again, keep an eye on what happens. So let me do make here. We have the ELF generated. I'll create another terminal, drag it here, and then I'll do make GDB. Right. So we see that our stack pointer is pointing here, which is hex ABC0 as expected. And then we see our instructions here. I'm going to go ahead and do NI for next instruction. It loads R1 with 7, which is expected. Then I do another NI, loads R2 with 3, which is also expected. And then I'm going to now go ahead and print the value at hex AB. So X space an address will print the value at that location, right? Now what I'm going to do is do an NI. And when I do an NI, what we expect is that these two would be pushed on top of the stack, right? So the stack pointer here should kind of auto decrement. And let me just go ahead and do this. And indeed, it has decremented, right? And it has decremented to BB8, and we'll again return back to our discussion about whether the decrement happened first or not. So we loaded two values, or rather this instruction here ended up writing 8 bytes. And why 8 bytes? Each register was 4 bytes. So R1 and R2 combined are two 4 bytes, which is 8 bytes. Okay, and the other thing is we were at hex ABC0. It seems to have gone down to hex PP8. So from 0, 4 down would mean ABBC, and from there 4 down would mean ABB8, right? And this is hex, obviously. All right. So we were pointing out at hex ABC. Oh, sorry. We were pointing at hex ABC0. Then it moved down to hex ABBC, and then it's now pointing to hex ABB8, right? So in that sense, then our value should be available at these 2 points. R1 should be here and R2 should be here. Now, if that happens, we'll be able to confirm whether it loaded the value first and then decremented, or it decremented first and then loaded the value. Okay, so we'll come back to that confirmation in a bit, but let's now go ahead and see what happens. So we do ni, and then we have 5 loaded here. We do another ni, and we have 5 loaded here. And now when I do ni again, we expect that R1 and R2 should be loaded back with the values that were stored on the stack. But before we do that, it kind of makes sense to take a look at what the stack is like. So I'll go ahead and print the value at AAB8. Okay, that is 0, which is fair. Then I load the value at C. Well, that's also 0. And then I load the value at C0. Everything looks 0 here. So when I do an NI, R1 and R2 are loaded with the values of 0, but that's not what I explained you. That's not what we expected. So what is going on here? Turns out the location hex ABC0 is not a writable location. So what happens then is, as the CPU attempts to write to that location, the writes are, in this case, happen to be ignored, and for those reasons the CPU also doesn't get to know that the writes didn't go through, right? It's kind of, you can imagine that the writes to this memory location are ignored, the reads from that are possible, but the reads are read back as 0. So what is going on? And again, we haven't answered the question about our whole talk about the stack. So our experiment here essentially has hit a bottleneck. It has hit a limitation, a blocker, and now we are supposed to resolve that. So one of the ways in which we can resolve this, in fact, you can think about what might be going wrong here. Let me just exit this. So somewhere our choice of stack is what is resulting to in this behavior. So what we're going to then do is go back to the README, and what I did was added these 2 documents here. One is the reference manual for the CPU or the board, M3 board that we are using, which is exactly this, the STM32 VL Discovery. So we need to look at the kind of the reference manual for this board and then figure out where is the readable and writable region of memory that we can make our stack pointer point to, right? And the reason we want to do that is we want the stack memory to be writable. That is the key. So what I'm then going to do is essentially go back to the README, right, and visit this this URL. So if I just kind of copy paste it, or command click on it, I have gone to now the reference manual, and this is the exact CPU variant that our board implements. Now within this, I'll go here in the list of what do you say, the table of contents, so to speak. I go to the memory map and then scroll down from there, and at some point they start to mention about the memories that the system has. Yeah, this is the part. But then at some point they start to mention where the RAM is, and that is what I'm looking for. I'm looking for where the RAM is. So they're talking about the flash memory. Yes, so embedded SRAM, there is 32 KB of it. It starts at the address of hex 2 million. So now hex 2 million is where it starts. I want some higher number. Okay, so let's go back here And let me just briefly open the foo.s. Perfect. So what I'm going to do is first off paste the hex 2 million here. Now we have to think about this a little more. So this was the SRAM, right? And they mentioned the start of the SRAM is 2 million, right? But this is where the SRAM is starting. And if I were to point my stack here, the stack would go downwards. It would decrement in the addresses, and there is no read-write region here. So what I then need to do is use some address from this region, from this 32 KB. And what I'm going to do is I'm just arbitrarily going to use like an address which is 4 KB above, or at an offset of 4 KB from the start of the SRAM address. Why 4 KB? Well, it's just an arbitrary choice. I know 4 KB will be in between the readable and writable region. So, my code is going to run. I'm going to be safe. Ideally, what people do is point it at the end of the SRAM, just so that you have kind of all of the SRAM to populate entries on the stack with, right? Okay, so then the choice I'm making is I'm going to change this 1 0 here to a 1, and that should make it 2 million plus 4 KB, or 2 million plus hex 1000. Hex 1000 is 4 KB, if I recall or remember correctly. So I'm going to go ahead and make this 1000. Perfect. No other changes required. We'll just go ahead and do make, and then let me create another terminal here, pull it here, then I do make GDP, then we do ni. Nice. And also notice that our stack pointer now is pointing to the location that I provided, which is 2 million plus 1 hex 1000. Okay, and then when I do ni again, R2 is loaded with 3. Then I do ni, and the values are pushed on top of the stack. Again, I'm able to confirm this because this number here has decremented by 8, right? It was 1000, went down to becoming this, which means 8 bytes it has descended or decremented by 8 bytes. Now again, we haven't yet talked about, or we are still about yet to answer the question whether value gets loaded first and then decremented the stack pointer, or it decrements first and then loads the value. Okay, we'll come to that in a bit. And what we're going to do now is essentially print the value at this memory location. So let me just do hex x and then this, and we see a 7 there, and the 7 is the value of R1 and R2 is 3. So what has happened here? So we have, first off, we are at the location hex 2 something something ff8, and we see a value of hex 7 here, which happened to be that of R1. Now this is interesting. Now what we'll do is we'll go ahead, do an ni again. Oh, actually, there was no need to do that, but I did it anyways. I'll do ni again just so that these two are modified. But what I should have done is I should have gone ahead and printed the value at the higher, okay, let me. So I should have printed the value of this memory location, which is FFC. So let me then go ahead and print the value of FFC. FFC is 3, and so we have 3 here, which is R2. And then, let's also go ahead and print 1000, and that should be 0. So again, this then is 0. Now, what it should tell us is, first off, we were pointing at this location to begin with. And when we performed this push R1 comma R2, what happened was that it took first of it decremented the stack pointer and then loaded R2, right? Then loaded R2 right here, then decremented the stack pointer again, and then loaded R1, right? So that is what has happened, and this should then prove that it decrements first and then loads. All right. And if you feel that this is becoming a little confusing, stay with it. It'll grow on you. You can perform a lot more experiments to kind of clear your understanding. Okay, so now let's go ahead and perform the pop operation. And I'll just paint kind of the state of the universe. So we had R2 here, and we had R1 here, which was 7 and 3 respectively. Right. And then this address is essentially FF8. This is FFC, and this is all zeros. And then I'm leaving out the 2 million, the base. I'm leaving that out in these numbers here. Now the question is, when we perform pop, um, how does it load back the value, right? So let's do that, and then we'll say ni, and we see that R1 and R3 are rightly populated again. So what it went ahead and did was it took the R1 value and put it here, and it took the R2 value and put it here, and that's how we have the 3 here and the 7 here, right? So this was then like the operation with the stack. What we reasoned about in this lecture was about that the stack pointer needs to point to a location that is readable and writable, number one. The second one is that the stack pointer is decremented first by 4 words, then the register is loaded, or the value being specified in the registers being specified in the push instruction, those are loaded. And the other thing we saw was the operation of load to the stack is from right to left, right? And then while popping, it's pretty much the same, except, well, the value being popped is loaded to the leftmost register first. And that's about it. And what I'm going to do now is, just to prove the point, we can give it like a list of registers here, and I'm going to just for fun load this value here, and also load this value here. Oh, sorry, load this value here. Let's go ahead and do this again, and hopefully any question or doubt you have, that should go away with this. Let me quit this, make GDP. I'll do an ni. Okay, I made a mistake. This should have been R3. So, excuse me for this. Let's go ahead and make this R3. Let's make this R3. Nice. Again, so make, just hit make, go here, do make GDB. I'll do ni. I have these 3 registers loaded. And just to kind of reiterate our concepts here, so we were originally pointing here. So we expect R3 to be put here, R2 to be put here, and R1 to be put here. So we'll go FFC, FF8, and FF4 respectively. Right? This is what we expect. So the numbers should be 7, 3, and 2. Right? Okay, and as we expect it to be popped out, that we'll take a look in a bit, but let me go ahead and do print. Oh, okay, I'm yet to push, but doesn't matter. Let's just go ahead and see what values we have here. So I'll put FFC, well, 0 FFC, 0 FF8, FF4. So all of these are 0. Now I do an NI and values are pushed on the stack. So this is the bottommost of the stack right now, or well, topmost of the stack. So I should expect 7 here. We have 7 followed by the next entry on the stack, that should be 3, and next entry on the stack at C should be number 2. Perfect. So this exactly matches up with this. We have 7 here, we have 3 at this address, and we have 2 at this address. And what we expect now is this will be popped back in the same order, so to speak, like R1 gets 7, R2 gets 2, and R3, oh well, R2 gets 3 and R3 gets 2. So let me then go ahead. Oh, actually, did I just, yeah. Let me just go ahead and do NI, which is loading each register with a phi. So just overwriting the values here. And now if I do NI, I should see 7, 3, and 2. Let's go. 7, 3, and 2. The stack position is ready as well. So with this, hopefully you're convinced as to how push and pop instructions work, and what is the role of stack pointer, and the fact that the stack pointer should point to a location which is readable and writable. And with this, I think we have the groundwork to now dive into starting to think about and reason about how a single CPU can execute multiple programs and how we can go ahead and write a scheduler. So with this, I'll see you in the next one. Bye-bye.